something was missing. So I found out something was missing, which is the gradient descent algorithm, and we need to cover it today. Without covering it, um, we would be lost out on a lot and a lot and a lot of things. So I would like anyone, maybe someone is there anyone you want to do like extra research to, and then I need you guys to tell me two things. What do you understand by activation function? Okay, three things: activation function, loss function, and gradient descent. Those three. Can anyone like help out? Sorry, I wasn't able to respond. Who is that? Can anyone help out? I just want to know like if there's any one of us who already have the knowledge of what gradient descent is. I was able to respond. All right. Of what gradient descent is, activation function, and loss function. Those three things.
Can we say it
Anyone?
in our own word?
Sorry?
Can we say it in our own word, like the way you understand it?
Yes, please. It's very
Okay.
important. It's very, very understand.
Okay. So for loss function, what I understand about this is like the difference between the actual minus predicted. Maybe you are expecting, say for instance, you're expecting maybe a dog, and maybe the model predicted a cat. So you have to compare the difference, like so the difference between the two, maybe the one is given like 0.8, the other is given like 0.6. So you just do the maybe like subtraction. So that's little difference. That is what they call loss function. My own word.
Okay.
Then activation function is just like a threshold that you set for a particular, maybe a particular easy node now. So the moment it gets to that particular threshold, it's performed that task. But as long as it doesn't get to that threshold, it will not transfer those information to the next layer. That's what I understand. Thank you.
Okay, you tried. Who else? Who else? So no one else has something to share. I like one more person to say something before I start. I just want to know like if you guys understand or like if you guys go out to like do like extra research or you just keep on waiting for me.
Good evening.
Yeah.
Yeah, good evening, everyone. So what I get by gradient descent is that gradient descent is an optimization algorithm. So I think we talked about it's the basic optimization algorithm we have for neural networks. So what it does is when you calculate the after the forward pass and the model calculates the loss. So what gradient descent does is that it helps to determine the best path towards what we call the global minimum. That is the point where there is minimal loss. So if you it's in 2D format, if you plot it, it's from the X and Y axis. It's more like it takes a U kind of shape, and it keeps the aim of gradient distance is to keep reducing the error until we have the least error during the training process. So after the forward pass, when you calculate the loss, it tries to find the next point that will lead to the least error. That's where with that information it can now do the backward pass, and then it comes back again and goes back like that. Then for the activation function, what the activation function does is it introduces non-linearity. So without the activation function, the whole neural network will be linear. So that's the major function of the activation function and the gradient descent. Thank you.
Okay, you're very correct. Can you guys see my screen? Can you guys see my screen? Hello?
Yes, we can.
Ah, okay. I don't know, for some reason I can't see it here. So you are correct, all right? You are correct. I don't know, I can't see my screen though. Hope you guys can see because I can't see anything. Well, let me try again. Sharing this. Okay, I'm sure you can see now. So, to build a complete neural networks model, a lot of things is needed. And last week I tried to like cover the basics. Today I'm going to like do a little more of the job of really moving, removing like all those mathematics and explaining very well. And I think if we spend time understanding this, it will be more benefitable to us than just rushing into like things. Because if you understand this very well, you would be able to jump into any part of AI, starting from computer vision, um, series models, LLM, whatever thing. If you understand these basics, it will make your life sweet. And that's why I need you guys to understand this before we get into like building any before we get into like building any LLM model. Sorry, building any computer vision model. So gradient descent and activation function is mostly what I'll deal with today, but I need to give like a recap of the steps for a neural networks model, right? So what is the step? First of all, we have input to what? To our node slash layers. So we have input going to these nodes. Um, hope you guys can see my screen, please. Sorry, can you guys hear me?
You can see your screen, sir.
Yes, we can see.
All right. Um, once again for last week, I literally didn't know that I was I've got like I actually put it in stage two when you guys were not promoted to stage two. So I didn't know like the assignment won't show until you are promoted to stage two. So I fixed that already. You can check your assignment and it to be showing now. Okay. So so let's say we have these neural networks model we want to build. In this case, this is a logistic regression model. It just has like a very simple one layer network. All right, something simple. So what are the steps? The first step is this: we put input to the node layer. So we have input on the node layer, which is this input that we have right here, starting from inputs x0 to input 1000 and something, right? 12,000 and something. The next thing we have what? After you put the input goes into where? Goes in here. And right here, we have what? We have the activation function. As this guy said, the activation function literally maps your input to the next node. And that it also does what? Introduce non-linearity. Non-linearity means without an activation function, basically what we're having is just we're having a linear model, no difference. Can I make this to stay longer? Anyways, so non-linearity means without activation function, we are just building a simple we are building a simple linear regression model. So it is activation function that gives us the ability to have what to build like a model that learns from parameters, a model that is not linear. It is activation function that helps us to build um, a binary classifier, and that depends on like whatever they want to do. So let's say, for example, we have a model. So let's say, for example, we have a model like this that is giving us maybe gives us like what it thinks, right? So it says the accuracy or the prediction is 900 and something or something. Man, I don't know how I'm going to use this thing. But you never. Let's say it says the prediction I have today is 900, right? We need to be able to map this thing to be between 1 and 0. It must be between this value. Because what we are looking for is to check if this is actually a cat or a dog. It's an activation function. Without activation function, we'll just be having the model just go like that, like just predict things, and it's just a linear model and it's not learning from anything. All right. So, and then we now have the loss function. We have the loss function. So the loss function helps us calculate the loss. There's cost function and there's loss function. Cost function, they are the same thing actually. So this loss function is just the difference between y at uh let me come here. It's different between y at different between our output and then our input. All right, I'm going to explain all this again today. And then so from the activation function, from the activation function, we calculate for costs, we calculate for loss, and then after calculating for loss, we run it through gradient descent. What does gradient descent do? Gradient descent helps us to manipulate these parameters, parameter W and parameter B. Mind you, parameter W and B is a parameter that we are choosing or that we are being given, and it is what we use. It's more like a knob, what we use to play around to make the machine learning model to learn or to give us like um different numbers in as results, right? So we have the gradient descent. Gradient descent is going to help us to reduce to play around with those knobs, and then we repeat the process until our result is close to the correct value. Our output is close to the correct value. What that means is, let's say for example, the output was meant to be 0.5. We keep on playing with these W zeros, W's, this weight. So they are called weight and biases. We keep on playing with the weight and the bias until this is equals to, or what the AI model is predicting is equals to the correct thing. All right. Okay. So these are the steps you follow. All right. And then so what are activation functions? I explained it. Activation function in neural network is a mathematical function applied. mm, oh, there's a pen here. Thank God. It's a mathematical function applied to the input of the neuron. It introduces non-linearity, enabling the model to learn or represent complex data patterns without it. Even the deep learning models will just act like what a linear regression model. So what am I saying? We have our inputs, we have our weights, and then we have our biases here, which is this one. These are bias. All right. This formula here is the same thing I did last week, right? Z equals W Wi plus X Wi times X, all right, then plus B. So what does that mean? When you see this stuff right here, this E, it means summation. So it means we sum everything together. All right. So it's summation of Wi times X and then whatever. So once we get this, we run it through an activation function. That's a function of Z, which is this result. and then from there we get our output. That's what activation function does. Now there are different activation function models. There's sigmoid, which is the most known. Sigmoid function. What does sigmoid function do to you? It makes sure your value, whatever number you get, does not go between 0 and 1. So if the number is above 0.5, then we classify it as 1. Number is below 0.5, then we classify it as 0. There's star function. This one goes from down here to 1. I think from -1 to 1. ReLU goes from 0 up, right? From 0 up, from 0 um down up, and then we have linear function, which is function of x. This one is just the simple one that we know, and then we have sigmoid function. But in your ML journey, the most you would always see is this one, which is always used mostly for binary classification, like cat versus dog. And then you would always see like ReLU activation functions, and then you would always see like this tan h activation function. This one you may not really use, except maybe if you are building something like let's say if I'm building something like an AI model that should predict that there's a probability that this is a picture of a I'm 90% sure this is a boy. I'm 90% sure this is a woman. You see. Now that's not, in such case, I'm not like building a classifier to say this is a boy or this is a girl. I'm trying to find like how sure am I that this is a boy? How sure am I that this is a girl? You feel me? So um so that's simple. We have different types of activation loss functions. Oh, I did a mistake here. So now, as I told you guys, loss functions help us to calculate the loss, which is y height. Y hat is our output minus the main result minus the real thing that we're expecting. So what is this real thing that we're expecting? Remember last week I told you guys about supervised learning. I told you guys that when we are giving our model, we are giving our model inputs, right? Input like a picture of a cat. We don't just throw the input to the model. We tell the model, yeah, this is the input, right, that I'm giving to you. And the correct label or the correct name of this thing is cat. So we're expecting that the model should know that this is a cat. So this thing right here, this cat right here you're saying here is exactly what we are talking about here. This is the right output that we're looking for. So if we say the thing output 1, that means it's a cat because we label 1 to be cat. So, but you're not going to give your model like, I'm not going to literally write like cat. Sometimes you write like 1 0 1 0. So if it is cat, we label it as 1. If it is not cat, we label it as, let's say for example, 0. So the label for cat is 1. So I'm expecting that for this particular input, the model should know that this thing that's predicted should be 1, should be above 0.5, which is literally 1. So if it is not 1, then it is wrong. So we subtract the output prediction minus the what? The minus the input prediction. And if it is not close to what we were looking for, then it is wrong. We have to now do the same thing again. We have to pass this thing, we have to get what we got here and pass it back. And then what are we going to do is that we play around with this W, this weight and the bias until we get what is close to what we have here. So in this situation, what happens is this is a cost function, this is a loss function, right? Which is correct. But now the issue is that this cost function right here, most of the times is not always like giving us the good result we're looking for. Most of the time when we calculate this thing, it doesn't like still give us a correct loss function. Like it's not, sometimes there's a little bit of error. That's why we now introduce a lot of loss functions. There's mean square error. So we get the error and then we square it. There's a lot of loss function out there. And it depends on whatever thing you're building, you can just choose. So there's mean bias error, which is like average prediction based showing overestimation or underestimation tendency. This is just the same thing that you saw right here. Exactly the same thing. But now with different algorithms. We try to use different algorithms to see how we can get the same result, right? We see how to see how we can use the same thing we know, but we apply like some little tweaks to see how we can make sure we get very good prediction. There's mean absolute error, there's mean squared error, right? There is this mean squared error takes your y minus your y height and then square it by 2. You see, square it by 2. Um Squared by 2, and there's root mean square, there's hyperloss. There's a lot of loss function. For classification tags, there's binary cross entropy, there's cross entropy, there's a lot of them. So in your journey, you'll be like coming across most of these things, right? So it just depends on what you're building, but it's the same thing. There's no difference, right? Let me correct this. It's the same thing, but they are, each of them are doing like different things to help us to get a very good cost fund loss function, a very good error function, so we can be able to predict if we are actually very close to what we are looking for. So having said all this, it now brings us to what? To gradient descent. Recap: we put our input, we each of the nodes has what they have weight and biases. All right, so we multiply the weight and the bias, we multiply the weight and the bias by the by each other. And we multiply the weight and the inputs, and then we add it by the bias. Then after this whole thing, we pass it through an activation function. As we pass it through an activation function, we do that same thing until we get to the output. Once we get to the output, we now apply a loss function. Now, what do we need to do? We need to make sure we update W and B to a point where W and B is literally low. The point where W and B, after we've manipulated them or more like turn them like a knob, we can literally get our result close to the main result that we're expecting. That's where gradient descent comes in. So all these things you are seeing here, I'm going to explain all of them down. I just had to put them here. So if you see, what are we looking for? Let's say, for example, this is a graph. All right. Uh, let's say this is a graph, right? This is a graph. In this graph, we are looking for where W and B is going to be somewhere down here. Because the more I manipulate them down to this point, the more I'm going to get very good results. And right now, let's say right now our W is somewhere around here. We need to be able to make sure we manipulate it until it comes down, comes down, comes down, comes down, and comes down. I'm going to dodge all these things. Then I'll explain to you later along the line. So that's what we are looking for, right? And that thing that we are looking for is called the global minimum. The global minimum. That's what we are looking for. So you see it in most articles, they write something like this. All right. So let's say W is down here. Now what is up here? Sorry, let's say W is up here. What is up here? It's just a very simple thing. It means the W has a big number, or has like a number that is not giving us what we're looking for. We're trying to reduce the W and play with W and B to a point where we are in a position where we are close to the correct thing, which is called the global minimum. Don't mind all these things, it's just small thing. For example, this one, for example, they just slope of a line. Just that we are trying to find the slope, like the difference between the two, we're just trying to find this slope here. And that's what is here. The slope in respect to W. All right, and this is called derivative. Like, don't bother about these calculus things. It's just like simple thing. There's no big deal here. It's just being used to scare you. Let me erase this thing. It's just being used to scare you. For example, this right here is just a learning rate, and I'm going to explain what it means. This is just derivative of J, all right, function J of W. Like, I'm just telling you, this is just finding slope of a line, which is just what is happening here. We need to make sure we reduce this slope until we get down here. All right. Okay. Assume I didn't say that thing. I'm sorry. Now let me explain it again. So imagine everything you're going to see. I'm explaining it as if you're a kid. All right. So I need you guys to assume like you're a kid. Imagine you're standing on top of a big hill and it's so far foggy, like you're not seeing well. You can't see the bottom clearly, but you want to get to the bottom, the lowest point. What are we saying? You want to get to the point. So you're on this hill right now, right? You're on this top of the hill. You want to get to the point that we are looking for, which is going to be somewhere around here, but you can't see. So the lowest point, that's the best. So we are trying to find this, right? The answer might be like the best model or the best numbers that make predictions more accurate. All right. So we're actually looking for the best model or the best prediction in our case scenario that's going to make our model more accurate. So what do? You look around your feet and you think, why is the ground sloping? Where is the ground? Which way is the ground sloping down the most? Then you take little steps in that direction. Like you repeat the steps, you look around. So let's say like you are this boy, for example. You're a boy here. You're a guy standing up here. You look around, right? You look front, you look for like which part of this slope, let's say the slope was something like this. Which part of this slope is literally like giving me the right, which part of this hill, which part of this slope is giving me the right, um, is sloping down the most. So I can literally like get down to where I want to be. You find that slope, all right? You step downhill, you go a little bit, you look again, and you step downhill. What does this mean? We are saying, let's say this is W and B. Mind you, we are playing with W and B. W and B is a value that is not being set. This value is not being set. It's just a random value you set at the beginning of your training. It's not being set by default. And then X is being set, so we can play around with X, right? So we want to be able to play with these two guys and get these two guys to the point where our model is doing so well. And our model is going to be doing so well down here, right? So what do? We look around. We look for number W we look for number W that is a bit close to what we are looking for, all right? And then we go down and look again. Is this thing like I'm not there? We go down until we literally get to somewhere around here. So you look around, step down here, look again, you step again. You keep on repeating the process. So, and that's exactly what gradient descent is. Gradient descent just a smart way for a computer to learn something, like how to recognize scatter, predict the weather. By first of all starting with a guess, like you are the hilltop, measuring how wrong that guess is, like checking how high you are, taking a tiny step in the direction that makes the guess better, like stepping down here, repeating until the lowest point or the best guess. So what are we saying? Gradient descent just is what help us do all these things. It looks around. Are we in the best guess? Are we like in the best position that our model should be? No. It goes down again. It goes down again. How does it go down? We keep on updating the hyperparameter. So why do we take little steps? The reason we take little steps is because we don't want to take too much of a high step where the model literally like goes too far and then it does what is wrong. Sometimes it's called like model overfit or like does some crazy shit. Let's say like the model is somewhere like we're trying to like we look down, we come here, we hit this point, then we look again, we hit this point, we look again, we hit this point, again we hit this point. So if let's say I was up here in this hill and I'm trying to like come down, and then I decide to take big steps and I jump down here, I jump down here, I jump down here. By the point I've jumped down here, I'm literally missing my point that I'm getting to. Sorry, missing my point that I'm getting to, and this is not what I'm looking for, right? So what do I do in this scenario? Is that I take small steps, very small steps. Look around, take small steps until the point where like I get to where I'm going to. So if you take big steps, you might miss the bottom. like jumping over it by mistake. If you take small steps, it might take longer, but it's much safer. At the same time, the small steps you are taking, if you take too much small steps, it will to like make you to take too much of a time, which is also not good. So you need to find the best number, right? So you need to find like the best number, like at what percentage do I take this step? At what percentage do I like jump? How many percent jump should I take? Should I take 100% jump? So let's say I set a number, I said like number 20. I say, okay, I'll be jumping in, let's say like by 20%. So I'll be increasing my jump, I'll be increasing my whatever thing in 20% difference. This right here, this number we are trying to increase by this number that we're using to determine how long we jump is what is called learning rate. Like I'm trying to break this thing little by little as a kid. Because without this, you'll be a prompt engineer. Without this, you'll be using ChatGPT API. You'll be doing like you'll be doing prompting ChatGPT and you call yourself an AI engineer. Meanwhile, you are just a random guy on the street that can prompt LLM. All right, so this is what is called learning rate. So we can call this step learning rate, the step size. It's like choosing the size of your strides. This one we're going to talk about this when I think by this week or by next week we should start talking about like strides is in computer vision. Okay, I'm gonna like ask you guys to I'm gonna explain this again, and I need you guys to explain to someone should tell me like if they understood what I said or what you understand from what I said if I move by. But I think I've literally like really broken it down. I don't think anyone should have an issue. Can someone like just tell me like what they understand if I move ahead?
Okay, so can you hear me, please?
Yeah.
Okay, so from what you explained, gradient descent is just training the machine, the computer to recognize an object, but then taking a gradual step and repeating a particular process of like uh, checking around with the scenario you gave, taking the small step, check around again, and until he's able to hit the point at which it is targeted to get to. But then the process might be slow or might be effective or will be effective. But if you take the bigger step, it can be faster, but then it'll be out of the lane and out of point. Yeah. Mhm.
Yeah. What else?
Okay, I think what I've learned is that uh, gradient descent is more of like tuning our hyperparameters in order to make our model more, to increase the learning rate of our model. I think that's what I've learned.
Yeah, I would like you guys to leave like I think I would like you guys to like leave all those big English like parameters. I need you guys to understand the thing from ground. Can someone else like explain? Victor.
All right. Um. So, gradient descent, as you explained earlier, is more of an optimization algorithm, as I said earlier. And what it just does is let's say you want to, I want to use your example. Let's say you want to go down a hill and you are looking for the best way to move down that hill. So you don't want to go too slow and you don't want to go too fast, because if you go too slow, you take time to get down to the hill. And if you go too fast, then you might move abruptly. So that's just what gradient descent is doing. It's trying to help you know the next best point you need to go. That's kind of optimized, that will lead you to that point of minimal minimal error. So those little steps you take are the learning rate. So if you have a is a very very small learning rate, then it will take you longer to train, which means a lot of computational cost. You spend more. Meanwhile, if you take a faster learning rate, then the model might not take time to learn the underlying patterns in data. So that's just what gradient descent does.
All right. I really hope you guys really understand these things because they are very important too. I think I may even decide to give you guys assignment where you guys go and implement it today. Okay, so we continue. So I'm gonna use a very, very different scenario and then we get into like the math thing, right? So let's say for example you want to bake cookie, right? You want to bake a perfect cookie, not too sweet, not too salty. You're adjusting one ingredient. Let's say you want to adjust sugar. You want to find the best amount of sugar that you put in this thing, right? Measure how close you are. All right. So let's say number one, the first thing you want to do is that you want to measure like how close you are to the correct test. So let's say you try putting 3 teaspoons of sugar in your cookie and then bake it a bit. And then you say, this is too sweet. Now, since the cookie is too sweet, you need to be able to measure how bad your cookie was, right? You need to measure how bad your cookie was. So let's say this is the cookie you're trying to do. The right cookie you're looking for should be very, very nice at this point, but your one was too sweet and in some way. You need to measure like how far is this from this, you know. Okay, let me use a linear function for example. So I think this way I can like you guys will see where linear regression comes in. So this is literally like where the main thing is meant to be. This way we can say, if your cookie, if the sweetness of your cookie is up to number 5 on this graph, then your cookie is sweet. But now you baked your cookie and your cookie sweetness level was somewhere around here. You baked again, a cookie sweetness level was somewhere around here. You baked again, and we're expecting it to be here. Oh. You baked again, it was here. So if you want to join, if you want to like say, okay, let me check how far it is, I can decide to like plot a line, a graph here. All right. And this is where linear regression comes in. Very, very simple. Can decide to plot a line and say, okay, this is it. So this is number 1, 2, 3, 4. This 1, 2, 3, 4. So I'm saying, oh, okay, this is what I'm expecting. So this cookie, the first time I did this cookie, it was here. So this is what I got. The next time I baked, the cookie was the sweetness was here. But the actual thing I'm looking for is here. So I want to know how far am I from the correct thing? What do? You now need to find a difference between this thing here and this. Difference between this and this. And that's where we have this formula, this simple line of a slope formula, which is x2 minus x1. Very, very simple. X2 minus x1. So we are just using this to find like what's the difference between this guy and this guy. How far is this thing that I got? So let's say this is our, let's say this is our x, what this like, let's say this is our x. For example, this is my x1, this is my x2. How far is this thing from this guy? Hmm? And that's where like slope of a line comes in. Y equals mx plus c. Now, what is this mx plus c? This line here, this graph you are seeing here, literally the graph I used to plot this thing. And this is what you see in neural network, right? But leave that aside. So I'm trying to find like the difference between this guy and this guy. How far is this guy from this guy? This thing I just explained to you right now is what is called the loss function. I'm finding how far the cookies is from the real sweetness. It's like this thing is simple. There's no magic, guys. There's no magician in AI. All this chat GPT, you are seeing all these Amazon Go. It's from these small, small things. There's no big deal here. Hmm? So this thing we are doing here is called the cost function. We are trying to find the error. So in this gap right here, in this space right here, is the error. From year to year is actually an error. Is wrong. From year to year is wrong. There's wrong something here. From year to year is wrong. Is an error. So how much is this error? How far is this value from what I'm meant to get? You see. But for me to get to this value, I need to play around with some things so I can get to this correct value. And that's what gradient descent helps us to do. Gradient descent is going to help us to make sure that we next time we adjust whatever thing that we put in here to increase the sweetness of this thing. We adjust that thing that we put the sugar to make sure the sugar level makes our cookie to be sweet up to this point. So when we plot our graph again, it will be something like this. You feel me, right? So now just simple thing, guys. Okay. So let's say you try putting two teaspoon of that sugar. So that thing is called the loss function. You can think of it like a cookie cooling meter, right? Measure how bad the cookie is. If the cookie tastes terrible, that's a high loss. You see, that's a high loss. Like that means the loss, the error was too much. So I can even put it somewhere around here. If the cookie tastes perfect, that means it's a low loss. That means I'm literally close to the value I'm meant to have. All right. Okay, so this loss in math formula, let's pretend it is sugar minus 2 squared. What is sugar minus 2 squared? Remember I told you guys something like y at, which is our prediction, minus y, and then we square it. This is squared error. Now this is just another sorry, I told you guys about this y at minus y. This is how we'll find our loss function, right? So this y needs to be a set value. So let's assume we need 2 spoons of sugar, which is now the correct thing. We need 2 spoons of sugar. We need 2 spoons of sugar to have the correct test. As we said right here. Right here. So the best amount should be 2 spoons of sugar. But let's assume we don't know yet. So let's assume we don't know we need 2 spoons of sugar here. We need to make sure we find 2 spoons of we find and adjust our body till we get 2 spoons of sugar. And then what we got was what? What we got was, for example, 4. Our predicted value was what? Was 4. So I can say my predicted value is 4 minus 2, which is equals to what? Which is equals to 2. You see me? You feel me? But this thing you are seeing right here, like this 2 here, that I'm literally like doing y at minus y square root of 2, it just means square. I'm trying to square like the cost function. I'm trying to square the cost function, the right thing here. And this is just another way of finding loss. There are a lot of several ways, as I told you guys. But I think I'm trying to explain, and you guys are going to like understand what I'm saying. So let's pretend that the loss function, the sugar, is the sugar that we put in, right? The sugar that we put in minus 2. This 2 is the correct value. Is the y that we are looking for, the main y here. The sugar here is the one that we don't know, but assume and just some way it's meant to be 2, but we don't know, right? And that's what is just here. So, and this is what is called the loss function. This is what is called lost. So we are 2. If I was doing this, I'm literally like, if I was just doing y at minus y, it's going to be like 2. So 4 minus 2, for example. So we are like 2 steps away from whatever thing we're doing. We need to make sure we are very, very close, right? So the best amount is 2 because that makes the loss 0, but we don't know yet. So let's say, for example, we add 2 here, right? So if I do 2 minus 2, that will be what? Squared 2. Square of 2. If you square 0, 2 minus 2 is 0. Square root of 0 is 0. And that will give us the correct answer we are looking for. But just assume you don't know it. You see, but at this point where I used 4 minus 2, and it is 2. Square root of 2. Now you see we are still far from the right thing. We are still very, very far from the right thing. So we have to play around with these cookies until we get what we are looking for. So what do we do? Imagine if you draw the loss as a curve, right? So the loss, like those values that we are getting, we draw it as a curve. How do I delete this? Okay, we draw it as a curve, like the loss was somewhere around here. You see. So let's say we draw that loss as a curve. Depending on how much sugar you use, it looks like a hill, right? Your job is to get the lowest point. That's the best cookie. So the slope tells you if the hill is going up, all right, or it's going down when you take a step. So use something called derivative. But think of it as what? How steep is my hill if I take a step? If the step is positive, right, then the hill goes up, and then you walk backward. So like if the hill goes up, then you have to like walk backward, so you get close to what you're looking for. If the step is negative, the hill goes down, right? Then you need to like walk a little bit forward. And that, my beloved brethren, brings us to this math right here. So every time you update your sugar, just guess that the new sugar is equals to the old sugar minus the step size times the slope. Mind you, why did I tell you guys about the slope? The slope is just this simple thing here. The slope of a line is just this simple slope here. The difference between this guy. They want to plot this difference. So let's say like the slope was something. Let's say I had something like this. Then I was somewhere around here. Want to find the slope. You can go and look at mathematics, how to find slope of a line. You see what we just do just to plot the difference, like this particular difference here, right? Oh, um, that's everything. So let's say this is it right now, and I'm here. I want to plot the difference here, and this is what is just the slope. And this simple slope we are seeing here is almost the same thing what is here. But it's just that in calculus they just make it hard and then see something like dy over the x. It's the same thing. There's no difference. It's just a formula for slope of just a slope. We are finding the slope in respect to x. You understand? We're trying to find the slope in respect to x. So so now the stepping size is what we call the learning rate, right? That's what we call the learning rate. How big are we going? How big are we going? How big are we going? So let's use numbers. So you start at 3 teaspoons. So the loss function is the sugar minus 2 raised to the power of 2. So we are saying 3 minus 2, which is 1 raised to the power of 2, right? The derivative is now the slope. Now the derivative, that's the slope, is going to be equal to what? 2 times sugar minus 2, right? Which is just this thing, right? Square root of this. 2 times sugar minus 2. So that will be equal to what? 2 times 3 minus 2, which is equal to 2. And as you can see, we are not close. We are not close to what we are looking for. We are still far. This is meant to be 0. This guy right here. We are still far from what we are looking for. So now we choose a stepping size. So like let's say like you take a big stepping size and then you now calculate it again. So we are now doing something like the 3, which is our sugar level, minus 0.1 times 2, right? 3 minus 0.1 times 2. This 3 is the sugar level. This 0.1 is our stepping size, our step size. And then this 2 is the correct thing. That will be equals to 3 minus 0.12, which is 2.8. So you're getting closer. You're a little bit getting closer to a perfect sugar. All right. Let me try to like tell you guys what's going on right here. So what's going on right here is exactly what is here in this place. Just right here. So this right here is our weight. We are trying to subtract it from what? The learning rate, which is this alpha you're seeing right here. All right. And then by this 2. And then we now compute it to make sure we reduce this W. All right. So so we repeat it again. So at 2.8, the slope is equal to what? 2 times this point 2 times 2.8 minus 2, which is going to be 1 point what, which is going to be what, 1.62. We are reducing. The new sugar is going to be equals to what, this minus 1.1, which are learning rate, times 1.6, which is going to reduce this guy. I will keep on reducing until we get really, really low. So, and we keep stepping down until you reach 2 teaspoons, which is exactly what we are looking for, all right, in this scenario. Because mind you, the normal this teaspoon we are looking for should be exactly 2, as we said right here, should be 2 teaspoons. So that's gradient descent. Pick a starting, guess like 3 teaspoons, measure how bad it goes, see which way it's going downhill, take a small step, repeat until you just get where you're looking for. So so what are we saying in this case? So let's say we have W, we need to update W, right? We need to update W. Let's say these are W. This thing you are seeing right here is literally just the same thing you do in Python programming, which is like assigning variable. So whatever thing that we have here, we will assign it to W, and that keeps on updating. And that's exactly what is sorry. That's exactly what is happening here. We get the result, we assign it, and then we keep on continuing to reach 0. So we pick W, which is our current value. Let's say our value was 2.8, or let's say it was 3. We minus it from what? From the learning rate, which is what? Which is 0.1. Then we multiply by 2, which is the slope. All right. Multiply by 2, which is the slope. And that's exactly what we saw here. This. Multiply by 2, which is the slope. And that is exactly what is here. W minus learning rate times change of dj in respect to W. All right. And that keeps on updating until we get a perfect value for W, and that will give us a better result. We do the same thing for bias. Do the same thing for bias. We minus bias minus the learning rate, and then we multiply by what? By the slope, the change of, that's the change, right? Alpha. So we multiply it by the change of, in respect to what? In respect to B. And this is gradient descent in a very, very layman's way. So with this, we will update our gradient descent until we get to the global minimum. Okay, so the last thing. So the hill that we're talking about here in this line is called JW. That means W, how bad our guess is, right? And then if the hill is high, if we're on the top hill, then it's bad. If we're on a low hill, then it's good. We are trying to go down, all right? So your goal is to get to the lowest point. What is W? W is like a knob that we can turn. It's a number that the computer is trying to adjust. The computer keeps changing W to make JW smaller. What is that we talking about here? This is W. This W here. We're trying to make sure this JW here, this change here is getting smaller. All right. So we need to make sure we play around with this until this get very, very small. And as we keep on updating this, it's going to be updating this value here. I think you guys, if you learn Python, you know something like assignment variable, which is something like this. I write something, I'm like 1 plus equals 1. So as it keeps on adding, the value is being assigned here. That's exactly what is happening here. All right. So this formula is just exactly what we're talking about. We're trying to manipulate and adjust W until we get the minimum value. So we pick W minus by learning rate and then by the slope. Now to understand this very, very well, you need to go and learn about derivatives. Start from like slope of line so you understand this very, very well. I think I've broken it down to a very, very beginner friendly level. So these are math W, which is we're updating W. W minus we take away from W, and then alpha, how big are we? That is learning rate, and then djw over dw is how steep the hill is here. That's the slope of a line. So what does it mean? You look at how steep the hill is, that's the slope, multiply by how big your step are, right? As the learning rate, then you step down here by subtracting it. That's exactly what we do here. You step down here by subtracting it, and then you look like saying, which way goes down, which way goes down? Oh, then you take another step, you keep on going. Look at the arrow. On the left side, the curve is negative, the right side. Um, all right. So so if for example we are getting like the slope is giving us a negative value, let's say like this slope, right, is giving us a negative value after like what we are doing. So the formula becomes like w minus a negative value equals to w plus something, right? Negative plus negative, negative times negative becomes plus. If you guys did like simple math in school, so that's going to be w plus something, and that will move right, which is going to move towards to the bottom. All right, so if we did math, we know that negative times negative gives you plus, negative times positive give you, I think, minus, right? So if the slope is positive, like if this guy right here giving us a positive value, then we know that we have w minus positive number, which is going to be negative. Negative times positive is what is negative, and then we'll move left, right, towards the bottom. Keep on moving, so it's going to keep on pushing you down, 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 down. So um so now what are we trying to do? We are trying to update both w and b, as I said. So for two values, we're updating w in respect digit in respect to w and b, and then for b we keep on updating it. So this is just, if you have two knobs w and b, you are just both the two by small small steps. Turn the sugar into a knob, right? Turn the salt into a knob until the cookie tastes perfect. That's the two things that we have. So this means that we don't just take one step. We take step, look back, step again, look again until we reach the lowest point. The whole image, that's the image I put around here. The computer walking down the hill, tiny steps, W tells how high it is. This guy tells which way the slope is, right? And then this tells the big step that we should take. It repeats until we get to the best answer. So in a nutshell, this is my JW. I'm trying to get to the minimum value of W. I take W, I update W, take away from W, then take a big step, and then this guy tell me how steep the hill is, then I step down here and I repeat it. So when I repeat it, whatever value I get here, I update it with this. Update it with this, and then once I update this, I repeat the process again. And that's exactly what I explained here. So we have our input coming, we have our X, we have our W, we have our biases, right? We are trying to play around with W and bias so we get a correct and the most close value to what we are looking for. So we get our input multiplied by the weight and the bias, and then we pass it through our activation function. Once we pass it through our activation function, at the end of everything, at the end of the entire neuron, we now find the cost function, the loss, right? We find the cost. How far is it from our output? And then based on that, we now use that, and then we use it to update W and B until once we update it, we update these numbers right here. Then we run the thing again. We run it again until we get like the correct value. So, children of God, I think that is it for today. I needed to explain this for you guys because without it, you'll be a vibe coder. You will vibe code all your life. All right. So I would like someone to tell me like what you've understood from everything, and I'd like you guys to go and do more research. I've literally broken it down like a kid, but I feel like some people don't still have like enough brain to understand it. So tell me like what you've understood, and yeah, go ahead.
Yeah, I've actually been raising my hand. I have a question. Like, can you go back to this slide I found that 0.1 kind of thing, sugar, the sugar slicer?
Uh, Which part? Yeah.
Yeah, this one. Yeah, this one. So
Mm.
I actually have a question from this the you start at something 3 teaspoons. So now what are we picking? Are we picking this slope, or we are calculating from the loss formula? Because if we calculate for the loss formula, we have like 3 minus 2, that's 1, and 1 is to the power 2, that's 1. And
Mm.
I don't know. So now we are picking the slope here. It is like 3 minus 2. That's so now we are having 2 as the slope here. However, you said we are looking for 2. Like we want to the correct answer that we are looking for is 2. So I'm thinking, have we not hit that 2 here when we calculated this slope? Like I want to get this before we like.
Yeah. So in this particular scenario, we are looking for tea 2 teaspoon. All right,
Yes.
and then we are literally starting from 3 teaspoon. So if you do like if we minus 3 from 2, that's going to be what? 1. Square root of 1 is not 2. Square root of 1 is what? Is not 2, right? So now based on this, we now find the slope. All right. And what we are looking for, even if we had hit 2.8 here, like you said, we hit 2, but we are looking for 2.00. We need to make sure we
Oh,
get
okay.
closer. So in ml, 2.8 is not 2. You feel me? 2.8, if we are, let's say if we are passing it from like to like a sigmoid function, 2 point is directly saying 3, or we are saying like 1. You feel me? So we're looking for 2.0. Do you
Oh,
understand?
okay.
Because 2.8 is like saying 2 teaspoon and then a liter and almost a full teaspoon, which is literally going to give you above the sweetness we're looking for. Do you understand?
Yes, I can. Okay, so
Okay.
another thing that I want to ask after like we continue moving, uh, deducting the learning rate. So what if at a point by deducting the learning rates, like how you are doing 3 minus 0.1 and the rest. So if we get to instead of eating that 2.0, what if it comes down like 1.8? What happened at that point?
Yeah, at that point when it comes down to 1.8, you now see that your value is not is lower than what we are expecting. It has gone past what we are expecting, and that's what literally happens when maybe you put like a too much higher learning rate. All right, or maybe like your value has gone past what we are expecting. What do you do? See that this value is not good, is not good enough for what I'm doing. You update the value again until you get what you're looking for. But at some point, this also leads to what is called like um overfitting, because you have literally like gone past what you're looking for, and the thing, let's say for example, it has gone to settle there. So what do you do in this case to avoid such scenario? You make sure you choose your learning rate in a way that something like that doesn't happen,
Okay.
right?
Mm.
Yeah, because your learning rate is in charge of playing around with things like that. But can I ask the question? Do you guys like understand like everything? I literally like I was not taught um machine learning this way. I literally like brought down all these things because this thing is something that you learn as an engineering student. You need like a lot of maths. Do you guys like understood everything I spoke about?
Yes.
All right. So it's already past 11. All right. I think we can call it a day. I think you guys you can do your assignments. Let me add one more thing. You can do your assignment, and by Friday would have another session. I'm really sorry, I didn't know that what I did was wrong. All right, I should stop recording. Do you guys have any